Good morning, everyone. Please raise your hand if the service or site you work on gets deployed to production at least once a week. Keep your hand up if it's deployed at least once a day. 3 times a day, 10 times a day, 20 times a day, 30 times a day. How about 40 times a day? Well, you guys have permission to play Candy Crush. For everyone else, Instagram deploys its backend server code around 40 times a day. Every time an engineer commits a change to master, it is automatically tested and deployed to our entire fleet in as little as 10 minutes, with no human interaction in most cases. My name is Michael Gorvin. I'm a production engineer at Facebook. And today I'm going to tell you how Instagram does continuous deployment at scale. Quick outline of my talk. Why do we even do continuous deployment? What is the point? Secondly, how did we go about implementing our system? Thirdly, what problems did we experience with it, and how did we address those? Fourthly, what are the key principles which make the system work? And these are the ideas which you can use in your own companies to achieve something similar. And lastly, what improvements are we thinking about doing? Quick bit of nomenclature before we get started. The term diff refers to a pull request, i.e. a proposed code change currently in review. The term land refers to committing a change to the master branch specifically. A commit I use to refer to the commit in master. And a rollout is a deployment to production. I use the terms rollout and deploy interchangeably. So the workflow is an engineer puts up a diff. Once it's accepted, he lands the diff. That results in a commit in master, and that gets rolled out. So why do we do continuous deployment? What are the benefits which make it worth the time and effort to implement and maintain the system? There are a few. Firstly, it allows our engineers to move fast, really fast. When engineers aren't beholden to fixed push schedules, they can get their changes into production whenever they want to. Within reason, we do strongly discourage landing changes outside of normal working hours for the sake of the on-calls. But otherwise, engineers can deploy their code whenever they want to. This means that they don't waste time waiting for the next push to happen, time which they probably aren't going to use very effectively, and which Kent Beck, the creator of extreme programming, theorizes will inevitably get filled with meetings. This also means that they can iterate multiple times a day. Sometimes you're working on a problem where you need to see your change in production before you can decide what to do next. Maybe you're debugging a complex problem and you need to keep collecting different bits of information as you follow the trail, or you're just squashing bugs which only show up once you enable your code in production. With continuous deployment, our engineers can do this as many times a day as they want, instead of being limited to a fixed number of deployments. When you're deploying tens or hundreds of changes in one go and something is broken, that's a big haystack you need to dig through to figure out what the bad change is. With continuous deployment, that haystack is a lot smaller. And in most of the time, for us, there is no hay at all, because we're deploying a single commit at a time, which makes it very obvious what the bad change is. This is also useful for problems which we only identify at a later stage. Sometimes we'll be informed that there's a problem. We'll find some metric or data which indicates that brokenness. From that, we can determine when it actually started, and we then have a look at what commits were deployed at that time and very quickly narrow it down to the suspect diffs. And thirdly, it means we don't end up with an undeployable mess. When you're deploying a whole bunch of changes at once and something is broken, then nothing gets out until you've identified the broken change and backed it out, which can get pretty messy with merge conflicts. With continuous deployment, you don't end up with a set of broken changes delaying everything else. And this also means that we can always get important changes out. We're always in a deployable state, and we're never stuck. So that's why we do continuous deployment. Lets our engineers move fast, makes it easier to identify bad commits, and means we're always in a deployable state. So how did we go about implementing this system? Now, the thing I'd like you to notice as I go through this section is the iterative approach which was taken. This wasn't something which was built off on the side, and one day we suddenly switched over to using it. Rather, this was a continual but intentional evolution of our existing mechanisms until they became continuous deployment. And I believe that is one of the main reasons why this was so successful. So how did things work before? Well, engineers deployed when they wanted to. They'd land a change in master. If they wanted it out now, they'd manually run a deployment. Otherwise, they'd just wait for someone else to come along and do one later. This was implemented as a Fabric script. For those who don't know, Fabric is a Python library and tool for basically SSH into servers, and it handled the process of creating a package, distributing it to all the machines, and restarting the web servers. Engineers were expected to know how to do a small-scale test beforehand. So they would actually run 2 rollouts. The first would target a single machine. Once that was done, they'd log into the machine, have a look at the logs, and if everything looked good, they'd then run a second rollout, now targeting the entire fleet. And we had a basic database and UI on top of that called SAURON, which basically held a log of rollouts, who had done it, what time, and which commit they deployed. Now, SAURON also holds what we call our operational locks. These are how we coordinate operations on parts of our infrastructure. If you're working on a component and you can't be interrupted, you would take the lock for that component, and that is how you communicated to everyone else that you were doing some work there. The engineer doing a rollout needed to take the right lock here, and that is how we ensure we didn't have multiple rollouts occurring at the same time. So the first thing we needed to do is we added a canary. Now, initially, this was simply scripting what the engineers were already expected to do. So instead of having to run 2 rollouts, the rollout script would simply prompt you, do you want to test on this canary machine? You'd say yes, would deploy to the canary machine, tail the logs for you. When you're happy, you'd stop the tail, and would then ask you if you want to continue to the rest of the fleet. At this stage, it wasn't making any decisions. It was simply automating the process. The next step was to actually inspect the health of the canary. So we collected the HTTP status codes of every request that gets served. Our Django application reported this onto a socket, and a script picked those up, tallied them, and then applied a set of very simple percentage-based thresholds. So less than 0.5% 5xx responses, at least 90% 2xx responses, and would simply warn you if those thresholds weren't met. It wouldn't prevent you from continuing the deploy. Now, we already had a test suite, but it was only run by engineers on their development machines. So when someone put up a diff, you had to take their word for it that they'd run the test suite and that everything was passing. And we didn't know that every revision we were deploying necessarily had a clean test run. So we got Jenkins to run tests in master. Jenkins is a continuous integration system. It basically watched the master branch. As commits were landed, it would run the test suite and then report this to SAURON. At this stage, SAURON simply kept track of the latest commit, which had passed tests. So in running a rollout, instead of it defaulting to the very latest commit, it would default to the latest commit, which had passed tests. We also added test runs on diffs. Facebook has a continuous integration system called Sandcastle, so we set this up to run the test suite whenever someone put up a diff or updated it. It would then report those test results onto the diff itself for everyone to see. Then we needed to lay some groundwork we were going to need for the automation. The first was adding states to the rollouts. So far, rollouts were simply a log of what had happened in the past. This added a state to them. So initially, they'd be in running state while they were in progress. If they were successful, they go into done state. Or if they failed, they go into error state. This meant we actually knew what the result of the previous rollout was. Then we added full commit tracking. As I mentioned, up until now, SAURON only knew the latest commit, which had passed tests. It didn't know about any other commits. Instead, we added a commit hook, which reported metadata for every commit to SAURON, and Jenkins then recorded that test result against each specific commit. This meant that SAURON now knew all the commits that had not yet been deployed and the test run status for each of them. And we added an abort button in the SAURON UI. So when a rollout is running, this abort button appears, and if you hit that, it'll change the state of the rollout to aborted, and the script occasionally checks this, and if it notices this change, will stop what it's doing. This allows us to remotely abort rollouts. Now, the main component of the SAURON UI is this table, which contains 2 types of entries, commits and rollouts. Commits are what you would see if you ran git log on the master branch. essentially a reverse chronological list of commits. We have the author of the commit, which links to their internal profile, the commit hash, which links to the repository viewer, the test run status as determined by Jenkins, the description, and then when it was committed. Rollouts are then slotted into this table directly above the commit which they are deploying. So there are the rollouts. They're identified by an increasing integer. We have the user doing the rollout, which now most of the time is Jenkins. I'll get to that. The commit information is exactly the same as the commit directly below it, because that is what it is deploying. The state is now the state of the rollout, so these are all done, i.e. they were successful. Targets is the number of machines we were attempting to deploy to. We actually have more than 999 machines. That's just a placeholder. And the deployed column is the number of machines currently running this rollout. So we can see that the entire fleet is running this latest rollout there. And we have the start and end times. The advantage of interleaving the commits and rollouts in a single table is it makes it easy to see which new commits each rollout introduced into the fleet. So we can see that this first rollout introduced one new commit, the second rollout introduced two new commits, and this third rollout introduced one new commit. We can also see that this commit at the top has not yet been deployed at all because there is no rollout above it. Now the really cool thing about this table is that the information in it is automatically updated every second. So you can always see exactly what the state of the system is. So I'll run you through what it looks like when a new commit gets landed and deployed. So at the moment, the very latest rollout was successful, and there are no new commits waiting to get rolled out. Someone then lands a change, and the commit pops up at the top of the table. We can see that it's currently in testing state, so we know that Jenkins is running tests on it. When those complete, we'll see the test status change to passed. Then the actual rollout starts. So that pops up at the top. We can see Jenkins is doing the rollout. It's deploying this new commit, and we're targeting the entire fleet. We also have that abort button on the right in case we need to stop it. Then the deploy count goes to 1. This is when it gets deployed to the CANARY machine. So we know that it is now currently testing on the CANARY, and if all those thresholds pass, then the real fun starts as it gets deployed to the rest of the fleet. And we see the count for the new rollout goes up as the machines get restarted, and the count for the previous rollout go down. When everything is fully deployed, we'll see the state go to done, and we're ready for the next one. Then we needed to automate some decisions which were currently still being made by humans. The major one was the commit selection. If there are multiple commits in master which have not yet been deployed, which one do we choose to deploy? So in this case, we have 3 new commits that have not yet been deployed since the last rollout. Now, we're always deploying directly from the master branch. We're choosing which revision to run git archive on to create a tarball to distribute. We aren't cherry-picking into release branch or anything like that. So we can't reorder commits, and picking a commit means you have to pick its ancestors as well. So the logic we implemented initially was very simple. Always pick a commit which had passed tests, pick as few commits as possible, and never pick more than 3 commits automatically. So in this case, because all these commits have clean test runs, we would pick 1 new commit. That would get deployed. The subsequent rollout would then pick 1 new commit, and the subsequent would pick 1 new commit. In this case, we've got some test failures. So we can't deploy that one. We can't deploy that one. So we deploy that one because it has a clean test run. That's 3 new commits, so we can still do that automatically. Then we had it fail the rollout if more than 1% of hosts failed to successfully restart. Up until now, only an exception in the rollout script would cause a rollout to be considered failed. This actually checked that most of the fleet was deployed to before calling it a success. And we had it warn if the previous rollout was not successful. So when you started up the script, it would check the status of the previous rollout in SAURON. If that was not successful, it would give you a warning, so you knew that things were not in a normal state. Now at this stage, running a rollout when everything was in a good state was simply responding yes a couple times. It would suggest the commit you deploy, you'd say yes. Do you want to test in the CANARY? Yes. Do you want to deploy to the rest of the fleet? Yes. That was boring, so we got the computer to do that instead. All those questions, which would normally be answered yes when everything was in a known good state, could be answered automatically. We got Jenkins to run the script. So instead of someone running this on their dev machine, Jenkins ran the rollout script, which gave us a UI to have a look at the logs, as well as live updates while it was running. And the engineer implementing this initially supervised Jenkins. They'd only enable this Jenkins job while they were at their desk watching things, until one day they didn't need to supervise it anymore, and we were doing continuous deployment. So that's how we implemented our system. We evolved our current mechanisms, automating them bit by bit, until they became completely hands-off. However, things were not completely smooth from the get-go. There were some kinks that we had to iron out before things were running smoothly. The first problem is that SAURON often looked like this. Someone would land a change which broke the test, and all the subsequent changes which got landed now also had that bad change and also had broken test runs. Or SAURON looked like this. Those blank boxes are where Jenkins hasn't even started testing those commits, and that third commit is still in testing state over a year later. I don't think it's going to get done. When we got into this state, someone had to A, notice we were in this state, B, identify and revert the bad commits, C, wait for the test to pass on the revert, and D, manually run a rollout of the revert before the automation would pick up again. That person was often myself, and I gained quite a reputation for being the reverter of diffs, and led to my former manager creating this to post to Twitter as part of a discussion about our continuous deployment system. So what did we do to fix this? Firstly, we made the tests faster. The tests were taking 12 to 15 minutes to run, and an engineer could easily put up a diff, get it accepted, and land it before the test had even finished running. So we got the test running in about 5 minutes, with a variety of optimizations, putting databases in RAM, increasing the parallelism, as well as profiling and optimizing some Python code that was heavily used during the tests. We made the tests more reliable. They would sometimes bomb out completely and not even report a result, usually with database-related problems. This was simply a case of identifying the most frequent failures, fixing those, and plastering over a bit with retries. And then we added the land lock. Now, part of the problem when we got into this state is that engineers would keep landing more and more changes, and we build up this backlog that we'd be then forced to deploy in a one go, which defeats one of the points of continuous deployment. So we added this land lock that we could acquire when we noticed we were in this state, and this would throw up a big warning when engineers tried to land changes. This allowed us to keep new changes out of master until we'd resolved the situation and things were operating normally again. So everything was going to be awesome now, right? Not quite. SAURON still looked like this 6 months later. What was going on here? Well, engineers still sometimes didn't wait for tests. What often happened here is their diff would have been accepted. They would then make a minor change to the diff, immediately land it, and it turned out that the minor change broke the tests. Or they didn't rebase. They created their branch a week ago, and on that week old base code, everything was good. But as soon as the new code got integrated with the merge, there was some interaction which caused the test to fail. Or there was some kind of external breakage. We do some tests which talk to remote services, and when those have issues, it can cause our test to fail. And while this isn't the fault of the diff author, it still puts us in a state where we don't have clean test runs to enable deployment. The solution here was to run tests before landing. Now, as part of Sandcastle, there is some functionality which we call Landcastle, where instead of locally merging your branch into master and pushing to the Git server, you instead create a Sandcastle job with a Git bundle or equivalent of your change. And this will then asynchronously create a branch, rebase your change on top of master, and push it to the Git server on your behalf. Now, this meant that we could also get Sandcastle to run the entire test suite. And if any of those tests failed, it would fail the land, and your change would not get into master. This meant that we were enforcing a clean test run on freshly rebased code before anything got into master. And this pretty much eradicated test failures in master. Now, we do have a few rollouts which fail each day, but often these are not because of bad diffs. In most cases, these are false positives on the CANARY thresholds, or a breakage of a system we rely on for our rollouts. When this happened, the on-call needed to manually run a rollout on their dev machine so that they could bypass the warning about the previous rollout having failed. Things got a bit weird with the commit selection, though. The problem is that we treated the previously attempted commit as being fully deployed, even though the rollout had failed. And so those previously attempted commits would not be shown in the list for selection, which was confusing for the on-call and meant that our announcements in RSC and elsewhere said things like deploying 0 commits, when that wasn't true. To fix this, we instead inferred the actual deployed commit by looking at the deploy counts. So we basically find the rollout with the highest number of machines running that, and we treat that commit as being the deployed commit. Now, because the on-call was running this in manual mode, they had to answer all those mundane prompts that we had automated. And they'd sometimes get distracted and forget they were running a rollout. And so we'd waste time just because the on-call hadn't pushed yes. To improve this, we added a retry button in SAURON. Instead of having to manually run the rollout, the on-call could simply hit this button in SAURON, which would launch the Jenkins job with a special parameter telling it to ignore the previously failed rollout and reattempt the same commit. This made dealing with these failed rollouts a lot faster and easier. So the tests catch most problems during development, and the CANARY catches the really bad stuff before it gets out to the entire fleet. But we do sometimes still deploy bad changes. And that's OK. We aren't a telecoms provider. We aren't promising anyone a 5 nines SLA. It's OK if things break from time to time. Now, that's not to say that we don't care about reliability. We do care about that very much and take it very seriously. But we take an approach of break it fast and fix it fast. And even with lengthy traditional release cycles, you still end up deploying bad code. And because of the lengthy release cycle, it takes you longer to mitigate that. The important part is to detect this quickly. So we already had good monitoring in place, but our alarms needed a bit of work to allow them to fire faster while still being very high signal, so that we could know about this very quickly. What we would do in this case is that we would then run a rollout of an older commit, which would create a new package, distribute it to all the machines, test it on the CANARY, and then restart the web servers. And so this took as long as a regular rollout. To improve this, we implemented a fast rollback mechanism, where instead we simply switched each web server back to the previous package still present on the local disk. This allows us to immediately jump into restarting the web servers, which we can do in 2 to 3 minutes, instead of taking twice that time. With these improvements, we typically respond to a bad rollout in less than 10 minutes, and sometimes in as little as 5. As I mentioned, we do occasionally have breakages in the deploy, and we can build up a bit of a backlog of commits waiting to go out when that happens. When the issue is resolved, the commit selection logic would select one commit at a time, and so it would take a while to work through that backlog waiting to go out. This also meant that new commits being landed had a lengthy delay before they got deployed. What would often happen in this case is the on-call would step in, and they would deploy the entire backlog in one go to get things operating normally again. But again, that defeats one of the points of continuous deployment. To improve this, we implemented automatic batching. This allows the commit selection logic to automatically deploy more commits per rollout when there is a backlog. The algorithm works like this. Now remember, we're always deploying directly from master, so we can't reorder these commits, and you have to deploy a commit's ancestors first. So this is a reverse chronological list of commits, so oldest at the bottom, newest at the top. For each commit, we look at how long ago it was committed, and we then set a time goal of deploying every commit within 30 minutes. So we then calculate how much time we have left until the goal for that commit expires. We then estimate how many rollouts we can get done in that remaining time, simply using a hard-coded estimate, in this case 5 minutes per rollout. And we then calculate how many commits we'd have to do per rollout to achieve that goal. So for the first commit, 1 commit per rollout would get us there. For the second commit, we still only have 1 rollout left, so we have to do 2 commits at once. For the fourth commit there, we have 2 rollouts left, 4 commits to go, so we have to do 2 commits per rollout. For the fifth one, we have 5 rollouts left, plenty of time, 5 commits to go, so 1 commit per rollout will get us there. We take the maximum of those because we want to meet the goal for every commit, but we still cap this at 3 commits per rollout to keep things reasonable. The advantage of this algorithm is that it takes the backlog into account as it changes. So as new commits get landed, those get taken into account. and we still deploy every commit in a reasonable amount of time while doing as many rollouts as possible in the time we have. The other problem is our deploys got slower as our infrastructure grew. Initially, the bottleneck for the deploy was the proportion of the fleet that we could restart at once, roughly 15%. But as we added more and more web servers, we ran into some other bottlenecks. The first was SSH agent. It was paying an entire core simply authenticating the SSH connections to the web servers. And the second problem was Fabric itself. Even though it does use multiprocessing, there's still a single master process which coordinates all the tasks, and that master process was pegging an entire core. The fix here was to switch to a distributed SSH system which Facebook has internally, and this got us back to restarting 15% of the fleet at once and doing rollouts in 5 or 6 minutes. So that's how we got things running smoothly. We improved the test runtime and reliability, implemented land castle, fast rollbacks, and improved handling of failed rollouts and backlogs. So what are the key principles which make our system work? And these are the ideas which you can use to implement something similar in your own companies. Firstly, you need a test suite, and it needs to be fast. I found for us the threshold is around 5 minutes. Less than that time, you don't really notice the time it takes for tests to run. By the time you checked your email, caught up on Facebook, the tests are finished and things can progress. But longer than 5 minutes, it becomes very obvious the tests are still running. And it slows things down in master in terms of getting clean test runs in order for deployment to start. So the tests need to be fast. Your test needs to have decent coverage. You need to be fairly confident that it's going to catch most problems during development. But it doesn't need to be perfect. Instagram is far from 100% test coverage. It just needs to be good enough. And you need to run your tests often. So during code review, before landing, and preferably such that it fails the land, as well as after landing, because you want to be sure that every commit you roll out has a clean test run. Secondly, you need an automated canary. You need an automated way to test changes in production at a small scale before it gets deployed to the entire fleet. The point is to catch the really bad commits, the things that are going to fail tens of percents of requests to your site. But it doesn't need to catch everything. Your canary doesn't need to be perfect. Instagram is still using these static percentage-based thresholds on overall HTTP status codes. It's good enough for us. It's probably good enough for you too. Start with something simple and improve it from there. Thirdly, have your automation handle the known good cases. If anything is not normal, just have it stop and let humans step in. The automation doesn't need to handle 100% of situations. It just needs to handle the common case. So have it inspect its environment, and if anything is not normal, just have it stop. Fourthly, I think a big barrier to automation in general is that people feel that they're giving up control, that they're not going to know what's going on, and they're afraid that the automation is going to run amok and do something stupid. And so it is important to make people comfortable. You do this by having understandable behavior. Your automation should have simple rules, and it should be easy to predict what the automation is going to do. Its decisions should never be a surprise to you. You need good visibility. It needs to be easy to see what it has done, what it is currently doing, and preferably what it is about to do. This is what the SAURON UI accomplishes for us. And you need stop mechanisms. You need ways for people to be able to step in, say, stop what you're doing, I need to handle this myself. We have the abort button in SAURON. If you take one of those operational locks, automatic rollouts won't start. And you can also disable the Jenkins job directly. And fifthly, you will still deploy bad changes. And that's OK. You just need to react to that as quickly as possible. So you need good monitoring so you know what's going on with your systems, fast alarming so that you know about these bad rollouts quickly, and you need a fast rollback mechanism so you can quickly mitigate it when it happens. So that is how you guide your implementations of a continuous deployment system. Now, this is working pretty well for us, but there are some challenges coming up and some improvements that we're looking to make it even better. The first challenge is going to be keeping up with the commit rate. Instagram is growing quickly, we're adding more and more engineers, and they'll be landing more and more changes. We still want to ideally deploy one commit per rollout, and so we want the rollouts to be fast enough to support this. One possible improvement here is to implement some kind of pipelining. So we could split the deploy up into two stages. The first would create and distribute the package and do the canarying, and the second stage would actually do the restart of the web servers. And those two parts take roughly the same amount of time currently. We could then have the second stage of the current rollout run concurrently with the first stage of the next rollout. So that by the time we finish restarting the fleet, we can immediately jump into restarts for the next rollout because it's already done distributing the package and canarying. This would effectively double our throughput. Currently, we test on a single machine and then deploy to the entire fleet. But there's a limit to the error rate that we can reliably detect on a single machine without having a bad false positive rate. To try and improve this, we're looking at adding more stages before we get to the entire fleet. So after we test it on one machine, then deploy it to an entire cluster, wait a little while, check some metrics, deploy it to an entire region, wait a little while, check some metrics, and then deploy to the rest of the fleet. The challenge here is doing this without slowing down deploys too much. And so this would almost certainly require the pipelining I mentioned previously. Then we'd like to get our canary catching more bad commits. There are two classes of problems which the canary doesn't catch well. The first are errors on lower volume endpoints. Even if you completely break a low volume endpoint, it gets drowned out by all the high volume endpoints, and we don't detect that. To improve this, we're looking at collecting per view function stats, so essentially each type of request we serve, and apply these thresholds to each of those. The challenge here is doing this in a way that isn't noisy and is not going to cause too many false positives. The second class of problem that doesn't catch well are interactions with our remote services. Let's say that a diff doubles the number of database calls that gets done. When the single machine is doing double the number of database calls, that's not a problem. But when the entire fleet is suddenly doing double the number of database calls, then your database falls over. So we're looking at collecting stats on the number of remote calls made and checking that those don't change too much with each diff. Now, the problem with these static thresholds we currently use is that they need to be relatively generous. The error rates do vary during the day, they vary from cluster to cluster, and they can also be significantly influenced by spammers doing weird stuff. And so they need to be generous enough such that they don't cause too many false positives. To improve this, we're looking at comparing our canary machines to a set of control machines. So we collect the same stats from a set of control machines in the same environment as the canary, running the current production version, and instead check that it doesn't change too much with the new diff. This would hopefully allow us to catch smaller errors while still having a good false positive rate. Most cases of the deploy breaking and needing to be intervened with are now bad diffs which fail on the canary. To improve this, we're looking at adding a canary step during land castle. So after land castle has run the test suite and those all pass, we'll then canary the change in a production machine and apply those same thresholds as the canary. If those don't pass, it would then fail the land. Now, this wouldn't replace the canary during rollout because we still want to test every package which we deploy. But it would help to keep these bad diffs out of master and stop them from breaking the deploy. So those are the improvements we're thinking about. Keeping deploys fast and catching more bad diffs before they get deployed to the entire fleet. So what should you take away from this talk? The main thing I'd like you to take away is that you can do this too. Continuous deployment systems don't need to be complex. They aren't only within reach of big companies like Facebook and Instagram. Start with something simple, evolve your current mechanisms, and focus on these key principles. A fast test suite with decent but not necessarily perfect coverage that are run often, during code review, before landing, after landing. A simple automated canary to test your changes at a small scale in production before being deployed to the entire fleet. Make people comfortable with understandable behavior, good visibility, and easy stop mechanisms. And expect that bad deploys will happen and be able to detect and react to those quickly. That, by the way, is the command used to deploy the Instagram backend. Thank you very much. Any questions? Yeah.
How do you determine which end users get canaried to?
It's completely random.
Just
It's just part of the load balancer pool and gets a random subset of requests.
good. Don't give everybody
Yeah.
that all the time.
So with respect to the canary systems, is that all organic traffic, or do you stimulate that with any kind of synthetic traffic as
No,
well?
it's all real traffic.
So typically, what is the duration over which a canary is tested?
Runs for about a minute. We do require a certain number of requests to be served by the canary. So if we do actually deploy like during off-peak times, the canary might take longer to get that minimum number of requests.
Oh. Another thing is, I saw in the batching slide that you would have different commits being deployed at the same time. So just wanted to understand how commits work for you. Doesn't a newer commit invalidate the previous ones, or?
So you're referring to the pipelining I mentioned?
Yeah.
So that would simply be preparing the next rollout while the current one is still in progress. So we have to create a package, distribute that, and then do the actual restart of the fleet. We could do part of that while we're busy restarting the fleet for the current rollout. They'll still be cumulative, and we wouldn't have two production versions running at once. It would just mean that the next rollout is ready to be restarted on the fleet by the time the current one is done.
So you don't try to do any optimization that reducing the number of restarts needed because there are so many commits that are already.
No, we want to do as many rollouts as possible because we want to deploy as few commits in each rollout. Any more questions? Cool. Thank you very much. Come catch me afterwards if you have any more.